After a long hiatus, I have finally found time to upload new videos. Thank you for your patience. We are going to take a detour from AI with a series of videos on functional programming and monads. Please leave your comments below. If you like what you see, click the like button and subscribe to the channel. There's a lot of confusion about monads, partial understanding and misunderstanding. I think it's because people from different backgrounds discuss and try to explain them. They bring their own jargon, history, and conventions, from category theory, computer programming languages. Each of these may have or lack specific syntactic sugar, software design patterns, and libraries implemented in different languages having desirable characteristics related to monads. I thought I would contribute to the long history of monad tutorials by publishing these videos. My background is in computer science and engineering. I did well in math, but I found it very abstract. To this day, mathematical notation puts a pit in my stomach and makes my eyes glaze over. However, computer scientists love to generalize abstractions. Software engineers actually love general abstractions too, because they let them reuse code and design patterns that have been proven complete, maintainable, scalable, and high quality. They don't have to reinvent the wheel. The most general abstractions are in mathematics. As I studied monads, I discovered that a single abstract pattern from mathematics could be applied over and over in different ways and circumstances. Not only can it create a complete programming language, it can help you be a better programmer in any language. A monad is ultimately about composition and recursive self-reference. It starts fairly simple, but it can get very complex. It can also take something very complex and express it simply. That's what makes it so useful to software engineers. So this video goes to the source of monads by introducing a branch of mathematics called category theory. The next couple of videos will link category theory to useful abstractions in functional and imperative programming languages. The videos after that will provide examples of monads and monad-like constructs in specific programming languages. You may have heard the phrase, "A monad is just a monoid in the category of endofunctors. What's the problem?" This, of course, merely introduces more jargon that requires explanation. Explaining monads this way is intentionally ironic, but it is derived from a book, Categories for the Working Mathematician. In this book, Saunders Mac Lane concisely described a monad as follows. A monad in X is just a monoid in the category of endofunctors of X, with product replaced by composition of endofunctors and unit set by the identity endofunctor. I gathered a more comprehensible understanding of a monad from the Wikipedia pages on the monad from category theory and on mathematical categories. The paper Monads for Functional Programming by Phil Wadler was also useful. Links in the description. So, what is a category? Well, a category consists of a few things. First, there's a set of objects. These are abstract objects that could represent numbers or cities or even musical notes. For now, do not try to relate these to objects you may have used in object-oriented programming languages. There is also a set of morphisms. Each morphism just directs from one object, we'll call it the source, to another, we'll call it the target. Now these morphisms have to follow certain rules. There has to be an identity morphism from every object to itself, and there has to be a way to combine or compose morphisms. To compose morphisms means to create a new composite morphism from existing morphisms. If you have two morphisms and the target of the first is the source of the second, you can create a new morphism whose source is the source of the first and whose target is the target of the second. Seems pretty reasonable. But what if you want to combine more than two morphisms? You could say, if you have three morphisms and the target of the first is the source of the second and the target of the second is the source of the third, you can create a new morphism whose source is the source of the first and whose target is the target of the third. But there's a problem with this. The more morphisms you want to combine, the more definitions you have to have, and the longer each definition becomes. It's more concise, convenient, and simple to define a composite morphism in terms of other composite morphisms. Of course, if you say a composite morphism is a morphism from a composite morphism to a composite morphism, then where do you begin? How do you get the first composite morphism? That's why you need an identity morphism. Now, you can define a composite morphism as any one of the following: an identity morphism, a composite morphism, and an identity morphism, assuming the target of the composite morphism is the source of the identity morphism, an identity morphism, and a composite morphism, assuming the target of the identity morphism is the source of the composite morphism, two composite morphisms, assuming the target of the first composite morphism is the source of the second composite morphism. Defining composition in terms of an identity and itself is a pattern you are going to see repeatedly in these videos. I have to stress that it is an idea that is important to category and also to the application of category theory to computer programming. Keep in mind that composition has four possibilities. We'll see this again later too. By saying that an identity morphism can be a composite morphism, we get a way to start any composition. Informally speaking, we can lift up an identity morphism into the space of composite morphisms. This allows composition to start somewhere but go as far as you want. It also allows decomposition to start anywhere but end eventually. A final reason this definition is important, that it makes it very easy to recognize composable morphisms. Whenever you are given one or two morphisms, there's a limited number of things to check whether they can be composed or not. For a category, composition has to be associative. If you want to compose three morphisms, then under the definition of composition, you can do it in two ways. You can compose the first two and then compose the result with the third. You can compose the last two and then compose the first with the result. If you get the same result either way, then composition is associative. Depending on how you define objects and morphisms, it may be possible to define compositions that are not associative, but those kinds of compositions will not let you form a category. What we've said so far seems pretty simple. Once you accept that there are objects and morphisms, it might be difficult to imagine how composition might not work or not be associative. But it's the habit of good mathematicians to ask weird questions. So here's two of them. We said the objects in a category could be anything. So can the objects in a category themselves be categories? We define composition in terms of itself. So if there can be a category of categories, then could a category include itself? It turns out the answer to both questions is yes. If you define things properly, you also get some results that are really useful in software development. If the objects in our category are themselves categories, then what would be a meaningful morphism between a source category and a target category? This is called a functor. And it is really a collection of morphisms, a morphism from every object in the source category to an object in the target category, and a morphism from every morphism in the source category to a morphism in the target category. That seems reasonable, but what about an identity morphism for a category? This is where things start to get complicated. A functor from a category to itself is called an endofunctor. An endofunctor includes a morphism from every object in the category to an object in the category, but not necessarily the source object. An endofunctor includes a morphism from every morphism in the category to a morphism in the category, but not necessarily the source morphism. I think of an endofunctor as a kind of altered or transformed view into the category. An identity functor is an endofunctor that provides a perfect view into the category. It includes a morphism from every object in the category to itself and a morphism from every morphism to itself. Our category of categories has objects which are themselves categories. It has well-defined morphisms, which are the functors, including identity morphisms, which are the endofunctors and identity functors. What would it mean for its morphisms to be composed? Based on the earlier definition of composition, a composite functor could be defined in terms of itself as one of the following. An identity functor. A composite functor and an identity functor, assuming the target of the composite functor is the source of the identity functor. An identity functor and a composite functor, assuming the target of the identity functor is the source of the composite functor. Two composite functors, assuming the target of the first composite functor is the source of the second composite functor. Remember when I said that composition has four cases? We see that again here. We've finally arrived at the definition of a monad, an endofunctor that can be composed associatively is called a monad on its category. I hope you saw a pattern in the way we defined a category and then a category of categories. This was the first step. I want to surprise you with how far this pattern can actually take us. For those of you who are not mathematicians, I expect this video was very theoretical and you wonder what the point of it all is. But please be patient. We'll get more practical as we go along.